Welcome to COMP382. We are going to continue our discussion about NFAs, and in this video I'm going to explain and prove the equivalency of DFAs and NFAs. So far I have actually explained, mentioned a couple of times that DFAs and NFAs are going to have the same power, they are going to have the same computational power, and so they're going to accept the same set of languages. The set of languages which are accepted by DFAs and NFAs are going to be called the regular languages. So here I'm going to prove this to you, that if we can create an NFA for a language, we can definitely create a DFA for that language as well. So this is, I can actually formulate the equivalency of DFA and NFAs as this theorem, that a language L is accepted by a DFA if and only if it is accepted by an NFA. So as you can see, this theorem actually uses the term if and only if. So if we wanted to prove the theorem, we have to prove two parts. The if part is going to be, we have to prove that, we have to show that if there is an NFA for a language L, there is also a DFA for the same language. And the only if is that we should prove if there is a DFA for a language, there is also an NFA for that language. So in this way, we can prove that both NFA and DFA are going to have the same power, so they are equivalent. The second part, the only if part, is easy to prove, basically because every DFA is an NFA, because if you follow the definition of a DFA, you can say that every DFA is a valid NFA, but not vice versa. Not all the NFAs are going to be DFA. So we have the main part that we have to prove is the first part. We have to prove that every NFA actually can be converted to a DFA. If you can have an NFA for a language, we can create a DFA for that language as well. So to prove this part, I'm going to actually do it using a constructive proof, and I'm going to do it over an example because this is by constructive proof, I mean I will show you that if you have an NFA for a language, you can create the equivalent DFA for that NFA as well. It means that a DFA that accepts the same language. And I will do the proof by exactly showing you how we can create a DFA from an NFA, or I should say, if you have an NFA, how we can create its equivalent DFA. Okay, so the whole idea of creating the equivalent DFA from an NFA is that we try to, when we are actually creating the DFA, we try to represent all possible situations that the NFA can be in them. So it's basically tries to create a DFA that has one state for all possible situations that NFA can be in at the same time. So how I'm going to do that, let me actually show it to you over an example. I have an NFA here. I'm going to create the equivalent DFA for that. The first step is that I would create a starting state, and that starting state is going to be, I will actually call it the same name as the starting state that you have in the NFA. And the reason is that the very first situation that you are going to be in when you are running your NFA is that you are going to be in your starting state, right? So this is one possible situation that your machine can be in. And that possible situation is going to be a state Q0. Then, if you actually think about it in this way, that all possible situations that your machine can be in is going to be all the possible subsets of all the states in your NFA. So when you are running your machine, your NFA, you can be, for example, in a state Q0, you can be in a state Q0 and Q1, you can be in you can be in the situation of being in a state Q0 and being in a state Q1, being in a state Q0 and being in a state Q2, all possible subsets. But when we are actually doing this constructive proof, not all of them are going to be realistic. So based on what is going to be your NFA, we will see that not all of these subsets are going to be useful. So to make our procedure faster, I'm going to just create those possible situations which we can actually be in. So let's do it here. If you just think about it, we are not going to work on a specific string. We are going to think about all the possibilities. So if you are at a state Q0, and just think about it in this way, what would happen if I see the symbol 0? I will do it for all of the symbols in my input, in my alphabet. So for example, the alphabet here is going to be the binary alphabet, only 0, 1. So I'm going to do it for all the possible symbols in my alphabet. So starting from Q0, what would happen if you see a single symbol 0? So this NFA tells me that I can either go to Q1 or I can actually go to stay at Q0. So it tells me that from Q0, I can have two possibilities. By seeing one symbol 0, I can either go to stay at Q0 or I can go to Q1, right? So this is going to be one possible situation. I will create one state for this possibility, for these situations, and I'm going to call that state Q0, Q1. I'm going to actually mark them this way to just make sure that I don't actually lose track of all the possibilities. So in my DFA, one new state has been created, and that state I am calling it Q0, Q1. Don't be confused. Q0, Q1 are going to be the state name from NFA, but the name of this state I'm actually just calling it Q0, Q1, which is showing the possibility in the NFA. And what is the transition? The transition is coming from Q0, and the label of the transition is going to be 1. The other possibility is that, okay, what would happen if I'm at Q0 and I see 1? So if by looking at your NFA, you will see that by seeing a 1, and if you are at Q0 by seeing a 1, the only possibility is that you stay at Q0. Okay, so I'm going to create. Do I need to create a state for that? I don't, because I already have a state that shows that possibility, that situation. So I will just add the transition and say that, okay, by transition 1, I will stay at Q0. So I'm done with all the transitions for Q0. Now I'm going to go and investigate what would happen if I am at the situation of Q0, Q1. This is going to be this state, right? Okay, I'm going to just, follow and check that for all the possible input symbols, what would happen? What are going to be all the transitions for this situation, Q0, Q1? So because I have two states, basically I have to just write down all the outputs. What would happen if I am at Q0 and I see a 0? What would happen if I am at Q1 if I see a 0? So for the possible transitions of 0, I should actually just follow this. If I am at Q0 and I see a 0, from the NFA you can see that you can either stay at Q0 or go to Q1. So all the possible all the possible states that I can be is going to be Q0 and also Q1. Not only that, you have to exactly do the same for Q1 as well. Say that what would happen if I'm at Q1 and I see a 0. From the NFA, it actually tells me that if I am at Q1 and I see a 0, there is no transition, right? So nothing is going to be added to this situation. So if you are at Q0 and Q1 and if you see a 0, the only other situation that you can go is going to be again being at Q0 or actually being at Q1. So the other state that, the transition that I'm going to add here for 0 is going to be go from Q0 and Q1 to Q0, Q1 in your DFA. Okay, be careful, this is different than NFA. In the DFA, I'm going to just simulate what would happen if I run the NFA. Okay, and for all the possible situations, I will create exactly one state. Okay, so this is for the transition 0. Now let's actually just see that what would happen for the transition 1. If I am at this situation Q0, Q1, I wanted to see that what would happen if I see a 1. So I will again do it one by one. What would happen if I am at Q0 and I see a 1? Okay, so you can see that at Q0 by seeing a 1, you will stay at Q0 in your NFA, right? If you are at Q1 and you see a 1, you will go to Q2. So I will actually get the union of all of these possibilities. So this is going to be going, if you are at Q0 or you are at Q1, if you see a 1, you will be either at Q0 or at Q2. So this is going to create a new situation for me, right? A new state in my DFA. So that's going to be called Q0, Q2. You can see that this is different than this situation. So I will create a state for that, and I am going to actually add this transition that goes from this situation with the transition 1. So I'm done with all the transitions for this state. Okay, so let's now check out this new state that I have. I have a state called Q0, Q2. I wanted to see that if I am at Q0 or I am at Q2 in my NFA, where I will end up, or what are going to be the transitions for me. Again, I will actually double check for all of the input symbols. So the question that you have to answer is that if I am at Q0 and I will actually see a 0, where I'm going to end up. By looking at the NFA, you will see that from Q0, by seeing a 0, either you stay at Q0 or you go to Q1, right? How about Q2? From Q2, by seeing a 0, you will see that there is no transition here. So you are not going to actually go anywhere. This is going to crash. So the only thing that you have here is going to be two possibilities. You can actually, if you are at Q0 or you are at Q2, if you see a 0, in the next step, you can be either at Q0 or Q1. Okay, because basically Q2 is not going to actually just go, move you anywhere, but Q0 can move you to Q0 or Q2. So we are done with the full transition here. From the situation Q0, Q2, by seeing a 0, you can actually move to the situation of being in Q0 or Q1, which you have a state for that. This is going to be the state that we have discussed before. So this transition is just moving you back to this state. So what about 1? Let me just clean up a little bit here. Now we wanted to see that where we are going to end up if we are at Q0 or at Q2 in my NFA and I see a 1. If you are at Q0 and you see a 1, you will actually stay at Q0, right? This is the transition. If you are at Q2 and you see a 1, there is no transition in my NFA, so you are not going to go anywhere. So in total, I can say that if I am at Q0 or Q2 and I see a 1, I will be, in the next situation, I can be only in Q0. So one more transition, this transition is going to be added. And from the state Q0 and Q2, I'm actually going back to Q0 in my DFA. Do I need any other situation to any other state in my DFA? No. The thing is, although all the possible situations that I can be in total are going to be all the subsets of this states Q0, Q1, and Q2, but only these 3 subsets are the feasible subsets for me. And so that they are enough to actually create the equivalent DFA. Now you can see that whatever string that you give to this NFA, if you check it and give it to the DFA, you will see that exactly that search tree that we discussed about will be simulated using this DFA, the DFA that we create here. So let me actually just clean up a little bit here. Maybe, okay, just before we finish this discussion here, I have one more question for you here. We created the DFA, but what are going to be the accepting state in this new DFA that we created? All of those states in the DFA that are representing at least one final state in the corresponding NFA, they are going to be accepting state. So here the accepting state in the NFA is going to be Q2, right? So in any of the states that you have Q2, you are going to call that one an accepting state. The only state that we have Q2 in is going to be this state, right? So I'm going to call this one an accepting state. And this is the only actually accepting state in your DFA. If you had some actually other states, like for example Q1, Q2, you would also call this one an accepting state. The reason is that it's just like, think about it in this way. It means that if you run your an string over this DFA and you end up to this situation, it means that you can be in Q2, which is an accepting state, right? So it's just like you're saying, yes, I can accept the string. So for all those states, accepting a state in the final, in the NFA, which are accepting, you call all those situations that have at least one accepting state in them in the corresponding DFA. To make it more easier to understand, to show that why these are going to be equivalent, let me represent something. Let me show that if I run an string over the NFA, what would happen? If I run it over this DFA, what would happen? I have actually represented all of the states in the in the slides. Whatever I'm actually representing here, I've already actually discussed. I just write down everything for you to make the slides readable. So this is going to be the final DFA. Here is the complete DFA. Okay, so which is exactly what I have represented before for you. Let me to make it actually easier to understand that what would happen, why they are equivalent really, let me actually represent that what would happen if I run this NFA over a string like 101, and what would happen in the corresponding DFA that we created if I run it over the same string. If you run it over, okay, let me clean up a little bit of space for you, and I'm going to show you that what would happen if I run this string over the NFA and what would happen if I run it over the DFA. Okay, if you run this string over the NFA, you started at Q0, right? By seeing a 1, you will see that you will stay at Q0. There is only one possibility, one transition here. And then by seeing a 0, you will, you can actually either go to Q0 or you can go to you can stay at Q0 or you can go to Q1 by seeing the 0, right? And by seeing the 1, you can, here you will stay at Q0, right? There is no other possibility for you. And by seeing the 1 here, you will, at Q1, you will actually move to Q2, right? So you are saying that this string is going to be accepted by this NFA because this one, actually this path is going to be accepting. Now, let me actually just show you that if you execute, if you run the same string over the corresponding DFA, what would happen? If you run it over the DFA, you started at Q0 again, right? This is going to be your starting state. You see a 0, sorry, you see a 1, the first symbol, right? And by seeing a 1, the only transition over 1 that you have here is saying that you stay at Q0. By seeing a 0, you will move to this state, right? The state is going to be Q0, Q1, right? This is the state that you have. And then by seeing a 1, you will go to this state, Q0, Q2. What does actually these situations are telling you? You will see that exactly there is actually corresponding, I mean, all of these steps are exactly representing the same thing, right? By seeing the 1, you started from Q0. By seeing a 1, you actually go to Q0. By seeing a 0 in the NFA, you can be in Q0 or Q1. And in the corresponding DFA, this state that you are moving to is exactly telling you that you can be either in Q0 or Q1, right? And then the other, actually, at the end, you actually move to either Q0 or Q2 in the NFA, and this is exactly the situation that you will end up to in your DFA. In the DFA, we represented all the possible situations that you can be in your NFA, and we created one state for each of them. Okay, so you can basically try to execute and run different strings, for example. Another string, let's just, I'm not going to actually do it. For example, just do it over the string like this, which is going to be rejected, and see that what would happen to the NFA, what would happen to the DFA. Just follow the path for both of them, and you will see that they are going to be exactly the same, representing the same situation. Okay, let's do another example here, creating the corresponding, I have an NFA here. I'm going to create the equivalent DFA for that. This is going to be an NFA because you have two transitions for Q1 over 0, right? One of them is moving to Q0 and the other one is staying at Q1. So this is going to be an NFA. I can create an equivalent DFA. Let me actually just answer this question just as an example. You start at Q0, right? The very first situation possibility that you have in your Non-deterministic finite state is going to be being at the starting state. Always when you start your machine, you will be in your starting state. Okay, then if you see your alphabet is going to be the binary alphabet. So for each of the possible input symbols, you are going to actually check all the transitions. At Q0, if you see a 0 in your NFA, you can see that you are going to move to Q1 and nothing else. So from Q0, by seeing a 0, I can move to a situation that I am at a state Q1 in my NFA. So I need a state for Q1. Well, how about 1? How about the transition 1? You can see that in Q1, if you see a 1, the machine is going to, in Q0, if you see a 1, the machine is going to crash. Basically, can be represented using a situation, right? That situation is going to be a state that you are not in any of the states Q0 or Q1. So I can represent it using a state, and I can actually show it in this way. And seeing that if you started at Q0 and if you see a 1 in your NFA, you are not going to anywhere, right? So I'm going to create one state for that in my DFA. You can see that it is represented as an empty set, or this is actually your dead state. This is the state that you are not going to anywhere. So the machine is crashed. The machine crashed, or whatever else you wanted to actually call it. So, and then I have now 2 new states in my DFA. I have to complete all the transitions for them, right? From, if you are at Q1, right, and you see a 0, where you can actually end up to, based on my NFA, I can actually see that I can either stay at Q1 or I can go to Q0. So this is going to be a new situation, right? You can either go to Q0 or stay at Q1. So I need a new state for that in my DFA. This situation or this state is going to be Q0, Q1. Okay, and the transition is called 0. What about the transition if you are at Q1 and you see a 1, where you are going to end up? By looking at your NFA, you will see that the only transition of 1 that you have is just staying at Q1. So I don't need another state for that. I already have a state corresponding to that situation. So this is going to be all the transitions for Q1. I have one more new state that I need to fill out the transitions for them. That state is going to be called Q0, Q1. To complete the transitions for this one, again, look at your NFA and see that what would happen if I am at Q0 and I see a 0. From Q0, by seeing a 0, you can actually go only to Q1, right? Not only that, you have also add all the possibilities when you are at Q1 and you see a 0. If you are at Q1 and you see a 0, you can see that you can either go to Q0 or go to Q1, right? Q0, Q1. So the whole possibilities that I have here are going to be Q0 and Q1. You can be either, if you are at Q0 and Q1 and you see a 0, in the next step, you can be either at Q0 or at Q1. So this is going to be a transition that just go back to the corresponding state in your DFA. How about 1? So let me actually clean up here and just write it down that what would happen if I am at Q0 and I see a 1. You can see that there is no transition. So it's just like here you are going to the empty set. But if you have also actually this possibility that you can be in Q1. What would happen in this case? If you are at Q1 and you see a 1, you will actually stay at Q1. So the union of all the possible states here and all the possible states here is going to be Q1, right? So if you are at Q0, it's just like think about it in this way. If I am at Q0 or I'm at Q1, and I see a 1, in the next situation I can be only in Q1. Okay, so I'm done with all the transitions for that state. How about this state? This is a dead state basically. It's just telling you that you cannot be in any of the valid states of your NFA. What would happen if you see a 0? What would happen if you see a 1? It's just like for both of them, you cannot be in any states, right? So I can just write down the transition for both 0 and 1. That's going back to this one. That's why this is going to be a dead state. If it's just like if you go to this state, you cannot actually leave it. If your machine crashed in your NFA, it means that it's going to crash, right? Or are going to reject the string. So just both of them are going to be equivalent. So I'm done with creating all the possible situation and states in my DFA. The last step is to just mark the accepting state. Look at your accepting states in your NFA. Only Q0 is an accepting state. So all those states that have Q0 in, I'm going to mark all of them accepting. The first one is this one, and the second one is this one. So I have 2 accepting states. And here is the more clean version of it. Okay, remember this NFA? We have actually already written down this NFA for the language of all binary strings that the third symbol from the end is going to be 1. So for example, strings like 100, 111, 110, 101, all of these strings 1100, all of these strings are going to be in this language, right? The third symbol from end is a 1, which is going to be this one. So try to create a DFA, an equivalent DFA for this one. One interesting property about the languages in this form, that are actually following this pattern, is that you can create all those languages that, sorry for the noise here, let me actually just, let the ambulance to pass. I'll try to shrink this part of the video later when I'm uploading it. Anyway, all those languages that are, for example, the language of all strings that the third symbol from the end is 0. If your alphabet is whatever else, the third symbol, the fourth symbol, the fifth symbol is going to be a specific, a specific symbol. All of these are going to have a very interesting property, that when you are creating an NFA for these languages, for example, if your alphabet is going to be binary alphabet, the number of states that you need is going to be, for example, if the Kate symbol from the end is going to be 1 or 0, the number of states that you need to design an NFA for that is going to be K plus 1. Just like this one, that the number of states that we need is going to be 4. 3 plus 1. 4 numbers of states is going to be enough. But when you are trying to design the equivalent DFA, you will see that the number of states that you need is going to be at least 2 power k. If your alphabet is binary, this is going to be exactly 2 power k. So the equivalent DFA for this NFA is going to have 8 2 power 3 states. Try it and you will see that all of those states are going to be required. This is a very actually interesting situation. All those, I'm actually showing it here, that all those languages that, for example, saying all binary strings that the Kate symbol from the end is equal to 1 or 0, doesn't really matter. The number of states in the NFA is going to be k plus 1, because the pattern is something like this. You just need k plus 1 states and just put a fixed transition here, and the rest of the transitions can be actually just written as all the possible symbols. Here is binary string, so it's going to be 0, 1. And the only final state is going to be this one. But when you are creating the equivalent DFA for that, you will see that you need 2 power k states. And we can actually prove this one. I'm going to leave reading the proof for yourself. I have written the full proof here. This is an interesting actually case. Just try to create the equivalent DFA for this example, and you will actually get the idea, and then read the proof here. This is showing all the possibilities here. And the reason basically is that in this specific actually pattern of languages, we need to show all the possibilities. That's why the DFA basically has all the possible subsets of all the possible sets of all the possible subset of the full set of states that you have in your NF. I think I've actually explained over, more than enough here. Okay, so we are almost done with explaining the, or discussion about the NFAs. So I proved you using a constructive proof basically that if you have an NFA, you can create an equivalent DFA for that. This shows us that NFA and DFAs are going to have the same computational power, and they are going to accept the same set of languages that we call them regular languages. And so someone might ask that why we care about the non-deterministic finite states. The reason is that you have already seen designing non-deterministic finite states are going to be easier than deterministic ones. The reason is that when we are designing the non-deterministic finite automata, we just care about what we want. It's just like you are abstracting away all the details of the computation and saying that, okay, this is what I want. This is the pattern that I want. Okay, but unlike that, when you are designing a DFA, you are basically designing the full machine that tells you that what would happen in all of the possible situations. So having this tool, basically NFA is going to be a kind of a tool for you that when we are talking about the languages in terms of the computational theory, the thing that we care about is that, for example, most of the time the question that we have to answer is that, is this language regular or not? Later on, we can see that there are some other actual sets of languages. Is this language, for example, context-free language or not? Is this language context-sensitive or not? So to be able to answer this question, that if the language is regular or not, if we can create a finite state for that, that's going to be enough. I don't really need to create a full DFA for my language. If I can create an NFA for that, that's going to be enough to show that, okay, this language is a regular language. I can create a DFA for that as well. But maybe designing the full DFA is going to take some time. It's going to be complicated, just like, for example, this example that I showed you, that designing a DFA for this kind of languages are going to be very complicated. because you have to create all the possible states, but designing the NFA for that is very straightforward. And that's enough. I just need to know that if the language is a regular language or no. So NFAs are going to help us to basically do a lot of mathematical proofs much easier over the regular languages, and when we are actually talking about the properties of regular languages. So this is something actually the topic that we cover in 2 weeks. So basically the whole idea of NFA is that just making it easier to do the proofs. So NFAs are more like a some tool to represent the regular languages. Kind of easier tool than the DFAs. So this slide is going to summarize the properties of DFAs and NFAs. What else? So I'm done with talking about the NFAs. The next topic that I'm going to cover is just an extension of NFAs that we call them Epsilon Nfa. In some textbooks, there is, no difference between Epsilon Nfa and NFAs. In your textbook, the textbook that I chose for this course, we have a separate section for Epsilon Nfa, so I thought that that's going to be better to just explain it in a separate topic. So in the next video, I'm going to explain the Epsilon NFAs, what's going to be Epsilon NFA, and again, I will actually show that Epsilon NFAs are going to be equivalent to NFAs and DFAs.